That's better. Okay. The task I've been given this evening is to explain the geology of the Cayman Islands in about 45 to 50 minutes. It's taken me 33 years to get to this point to be able to explain that geology. So I can't explain everything we've done. All I can tell you is that as a geologist, I'm going to give you a summary of what I've learned. This is based on an enormous amount of field work. We've looked at just about every rock on these islands, every type of geological test that we can do, ranging from scanning electron microscope work, electron microprobe work, many, many different types of geochemical analysis, stable isotopes, radiogenic isotopes, all goes into this and becomes part of the picture. Don't panic. I'm not going to give you all the nitty-gritty details of all these analyses. If I did that, you'll be here for a week, at least. So I'm going to give you a summary. I'm going to talk about the geology of the islands and hopefully explain some of the things that may have puzzled you about the rocks that you look at and give you some information about the islands on which you live. I would like to thank, first of all, the Water Authority that sponsored me coming here, the National Trust, and of course, my own university for allowing me to escape for a week to the islands. What I'm going to do here, I'm going to start off by looking at the geological setting of the Cayman Islands. I will then have to define some basic geological terms. You're going to find as a geologist, I have a whole different vocabulary to use. If I slip into geological jargon, you probably would not understand me very well. Some people would. But if I do that, put your hand up and tell me to start speaking English again, please. We're going to look at the geological framework of the islands and then look at the economic value of the geological knowledge and the impact it's had on the development of drinking water on the Cayman Islands. When I do my work here, I do it both from a pure scientific perspective, some very esoteric studies of various aspects of the rocks, but also I do it with a view of a practical application. And the practical application here is with respect to the drinking water. In terms of the Cayman Islands, you're very familiar with where you're sitting. You're sitting on the Cayman Ridge. Cayman Ridge stretches from the Sierra Maestra across here, across the Caribbean. Off the southwest corner of Grand Cayman, there is an active spreading center. And over the last 4 or 5 years, there's been a number of scientific expeditions in which many submersibles have gone down and looked at this and have demonstrated that this is truly active. There is magma coming up here, and the magma that comes up here pushes this part of the seafloor that way, pushes this part of the seafloor this way. From the north end of this spreading center, there is an Orient Transform Fault that stretches across here, and here we've got the Swan Island Transform Fault. These are active systems, and you'll see the implications of that shortly. If I take a cross-section that stretches from the Sierra Maestra across here, then here you see the Sierra Maestra, Cayman Brac, Little Cayman, and Grand Cayman. The information that we have is that not only do you have the faults running this way, but there are probably faults that are cutting across the Cayman Ridge. Certainly there is one between Cayman Brac and Little Cayman, probably another one at the east end here, and there may be one or more between Little Cayman and Cayman Brac. So this ridge, in effect, is segmented into distinct blocks. Each of those blocks can behave independently, as we're going to see. And the other way of looking at this, and one way of thinking about it, here's a scale of 5,500 meters depth here. Grand Cayman, although you always look at Grand Cayman as being fairly flat, you're actually sitting at the top of the mountain. It's just that most of the mountain is underwater. If we look at Google Earth and Google Oceans, which is a great resource in this because you can peel away the water and see the seafloor. Here's Grand Cayman, there's the spreading center, and there is where the Orient Transform Fault cuts across, and this drop off into the water depths of the Cayman Trench, which are often in excess of 7,000 meters. And here is the faults probably cut in between these islands. The reason I say probably is that we simply don't know. There hasn't been enough work done on the ocean floors in these areas. They haven't been mapped in enough detail using different geological techniques to allow us to say for sure whether or not there are faults there. So we have to infer their presence from the geology on the islands. These three islands sit on, from a geological perspective, sit on the south margin of the North American plate. And here we have the Caribbean plate moving this direction, North American plate moving this direction. Hence, you have earthquakes. And one of the ways you can track the earthquakes, if you're ever interested in it, and the reason this does not look particularly clear, is I've taken this straight from the site. If you type in Google, United States Geological Survey, page will come up, type in earthquakes, and it will come back and say which part of the world. You type in Cayman, and it will come up and give you a full listing of all the earthquakes that have affected Cayman. And this is a list I picked between 9 and 21 years ago, just to give you an idea of what's going on. And as you can see here, these then correspond to the map view where they show you the focal points of the earthquake, and based on the size of the earthquake, the area that would be affected by it. So here, this explains why you get so many earthquakes here in the Cayman Islands. Some of them are based around the spreading center, some are based along the Orient Transform Fault. And these really only show the type of earthquakes in which you would feel. And there are actually many, many more earthquakes, on the average of something 1 or 2 a week. But most of them are so gentle that you will not feel them. So this is why you get the earthquakes. You are in a tectonically active zone. In terms of geological time in the Cayman Islands, this is all the standard geological terminology that I have to deal with. In terms of the Cayman Islands, the rocks of the Cayman Islands, and here, please understand, I'm only showing the ages of the rocks that occur at the surface of the islands. So I'm not showing the age of the rocks underneath sea level or where I drill down. But for example, if I want to find some of these oldest rocks, and the oldest rocks I know about on Cayman Islands, which we've dated reasonably accurately, is at the very east end of Cayman Brack. In the foot of the cliffs, at the east end of Cayman Brack, the rocks there, we've dated at between 28 and 30 million years old. And all the other rocks you see on the other islands are at various ages in between. Do not worry too much about this terminology. If you want to, you can go and look it up. But in these islands, we'll see representative of Miocene, the Pliocene, and Pleistocene rocks, and that's what I'm going to take you through. If you look at the rocks of the islands, and the question you may have is all of these rocks that you walk across, where did they form? How did they start life? Well, the easy answer is to look at this picture. This is a picture taken in South Sound. It shows all the coral reefs, carbonate sediment. Carbonate sediments is anything that's made up with components such as calcite, aragonite, that has the formula CaCO3. If it's got the part of the formula CO3, that's a carbonate rock. So this is all carbonate material here, and with the passage of time, that is going to be transformed into hard rock. And that's what you're going to see here. So every bit of rock that you see on these islands started life in an environment similar to this. Sometimes it doesn't look like that when you look at the rocks, but this is what it really is. I'm going to have to define a few geological terms because I'm not sure of what people's geological background is, and if I don't do this, I'm going to get people lost very quickly. Two rock types that you have to worry about, or we worry about. Limestone. And the limestone is formed of the mineral calcite or aragonite. Both of these minerals have the chemical formula of CaCO3. The reason they are two different minerals is that they have two different atomic structures. And a mineral is defined on the basis not only of its composition, but also on the basis of its atomic structure. And just to show you how complex this can get, these shells in here, these bivalve shells or clam shells as you would know them, they've built their skeletons of aragonite, whereas most of the sediment in between those shells would actually be formed of calcite. And this becomes important later on because aragonite, even though these are both formed of calcium carbonate, Aragonite is more unstable than calcite. So if I start rainwater falling on aragonite, it will dissolve it. It won't dissolve calcite. It's just because of the atomic structure. The other rock type that we find very frequently on the islands is the rock dolostone. And dolostone is formed of the mineral dolomite, MgCaCO3 twice. The term dolomite is one of the oldest terms that we have in geology. It's at least about 210 years old. It's named after Count Deodat Dolomieu. And he worked in northern Italy and tested the rocks and showed that they were formed of this composition. And for those of you who've been in Italy and been to the Dolomite Mountains are also named after the same gentleman. It gets a little bit confusing because if you're in Europe or you're dealing with a European geologist, then both the mineral and the rock is called dolomite. If you're in North America, the mineral is called dolomite and the rock is called dolostone. As geologists, we like to confuse people. We confuse ourselves in many occasions. So we at least, if we only got 2 terms for something, that's good news. We typically have 5 or 6 terms for everything, just to make life interesting. So the 2 main rocks that you're going to find on this island, dolostone, limestone. We understand how these rocks form. We do not know how dolomite forms, even though we've known the term for over 200 years and many, many people have worked on it. With the exception of a few peculiar places on the Earth's surface, dolomite does not precipitate directly from seawater in the modern oceans. And we simply don't understand it. In most cases, dolomite forms which starts life as limestone like this. It gets buried in the earth, and by various processes, which, as I say, we're still trying to work out, you actually transform this calcium carbonate into a magnesium calcium carbonate. And one of the reasons that we do not understand how it forms is nobody has yet been able to grow a crystal of dolomite in the laboratory at low temperatures and low pressures. If you want to grow a crystal of dolomite in the laboratory, you've got to have at least 100 degrees Celsius water, and it's got to have high pressure. So we've got a bit of a mystery. We've been trying to work this out for 200 years. The geologists were either slow and stupid, or there is truly a problem here. I prefer the latter explanation. The other terminology, another term that you're going to hear me use is the term formation. If you're looking at geography, you're looking at the surface of the Earth, you're looking at the spatial distribution of things across the Earth's surface. As a geologist, I have to add a 3rd dimension. Third dimension is depth. As I go down into the rock sequence, that 3rd dimension is a measure of time. And in order to deal with that, because I've got thousands of meters of rock, as geologists have to deal with, then we define the term formation. In the simplest context, the formation refers to a package of rocks that are all similar to each other, but different from the rocks in the packages above and below. So, for example, if I go into the quarry at Pedro Castle here, this was a photograph taken about 5 or 6 years ago. It's now getting badly overgrown. You can hardly see this. But here you can see a distinct line cutting across the quarry. This is what we have called the Pedro Castle Formation. This is why it's called the Cayman Formation. The Cayman Formation is formed almost entirely of dolostone, not all of it as we've now discovered, but it's mostly dolostone, whereas the Pedro Castle Formation is formed of dolostone and limestone. And the idea of this is it's simply a means of communication. So if I'm talking to geologists and start talking about the Cayman Formation, they know what I'm talking about. The other formation that you commonly see on this island is the Ironshore Formation. You're all familiar with this. This term Ironshore Formation goes back to the person that originally, the first person that looked at the geology of these islands, which was Charles Matley in 1924. He was a geologist that was based in Jamaica, attached to the Jamaican government, and of course Cayman at that time was administered through Jamaica. So I don't know what he did, but they sent him over here and they said, go over there, map the geology, And that he did, and he did a remarkable job. He only spent about 4 or 5 days here. I don't know how he managed it. But he did a remarkable job. Some of the basic maps that he produced still are pretty good today. We've changed them a little bit, but not a lot. And one of the formations he named was the Ironshore Formation. The term Ironshore was taken from the local Caymanian name for the hard rocks that you find along the western shoreline. And at that time, the people used to call that the Ironshore. So he took that name and named the rock here. And Hendrik, suffering through another day of field work with me, one of his jobs is to act as scale for my photographs. So it's a new training that he has. Very skilled. And here you can see the Ironshore. The Ironshore is formed entirely of limestone. So these are names that I use, all right, and will use. The other term that I'm going to use here quite often is the term of unconformity. An unconformity is a surface which is exposed or has been exposed to the atmosphere, and it undergoes weathering. So when I show you a picture like this of Cayman Brack looking to the west, the cliffs at the east end, you see a land surface. When I look at that, I say unconformity, because this is when the rocks are above sea level. They are being weathered, they are being broken down, they are producing a weathered surface. You've got deposition taking place here, we've got weathering taking place here. And this has a very important impact on the entire story of the geology of the Cayman Islands. Now, if you look at that surface, you may say to yourself, well, what would that look like if I saw it in a rock face? Well, and I'll come to that in a minute. Sorry, I got ahead of myself. Here, what we can do with these surfaces, modern ones, this is a digital elevation model based on data from Lands and Survey, showing what this surface looks like. The high end here at the east end dropping off to sea level at the west end. And we use these models today. We've been doing quite a bit of work with this to try and identify the type of features that would develop on one of these weathered surfaces. We now have to look at what we call the stratigraphy of the Cayman Islands. The stratigraphy refers to these different units, and also stratigraphy literally means the tying together of different rock units in different areas. So if I'm on Cayman Brack and identify the Pedro Castle Formation, I come to Grand Cayman, identify the same formation, then I'm going to link those together, say that they're the same type of rock, probably formed at the same time. Starting on this, just to show you the formations we've used, the Brack Formation. The only place that you can see the Brack Formation exposed is at the very east end of Cayman Brack. In the foot of the cliff faces there, you can see it. You do not see it exposed on Grand Cayman. If I want to see it exposed on Grand Cayman, I have to drill. If we're in this area here, I probably got to drill to a depth of about 400 feet before I can find it. Cayman Formation, the Brack Formation formed about 30 million years ago during what we call Lower Oligocene. There is an unconformity developed on this. Cayman Formation, this is the most widespread formation of any of the rock units. We see this over most of eastern half of Grand Cayman, and this is a formation that forms most of the bluff on Cayman Brack. This is Middle Miocene. In the Pedro Castle Formation, there's another unconformity here. Pedro Castle Formation, not widely exposed. The only place we see this exposed is around Pedro Castle, where the name comes from, and also a small exposure on the west end of Cayman Brack. And then the Ironshore Formation, which you find exposed over somewhat exposed over most of the western part of Grand Cayman, and on the platform, the flat platform that goes around the edge of Cayman Brack. Brack Formation is limestone and dolostone, Cayman, dolostone, Pedro Castle, dolostone, and this is just a list to show you some of the fossils that you find in these rock units. The story about how the Cayman Islands evolved is really related to sea level. This sea level here this black line indicates the position of modern day sea level. This would be rising, falling sea level. So if I'm on this side of this line, sea level would be way above where it is today. If I'm on that side of the line, sea level is below where it is today. And what you notice here, and it makes sense, is that when this part of the curve is above modern sea level, then we've got deposition. So here, when the sea level is very high, we've got deposition, and then the formation of the brack formation. At this point, about 30 million years ago, in the middle of the Oligocene, this has been estimated to be one of the single biggest and fastest drops in sea level that the Earth has ever experienced. The estimates for the drop here is something anywhere up into the order, I've seen estimates as high as 250 meters that took place over a very short period of time. We have trouble getting these numbers accurately, but in parts of Australia, in parts of North America, there is fairly good evidence that's at least in the range of 200, 250 meters. So tremendous drop in sea level. And in case you're wondering why do you get such a drop in sea level, then any time that the ice caps in the Antarctica, North Pole start expanding, the ice grows because it takes water out of the ocean. If you take water out of the ocean, sea level drops. If the ice caps then melt, the water goes back in the ocean, sea level goes up. There are other ways that it happens, but that's the main one. So here we have weathering. This would be when the brack formation underwent weathering as it's exposed to the atmosphere. Later on, sea level rises again, not to the same level that we see here, but rises again, and we get deposition of the Cayman Formation. The age of the Cayman Formation we are not certain about, because this has proved very difficult and so far I would say almost impossible to date accurately. We know it's Miocene, but we just don't know whether it's lower Miocene, middle, or upper Miocene. We're having trouble with that. At this period in time here, in the upper Miocene, sea level dropped again. This is what is called, in geology, we call it the Messinian sea level crisis, or salinity crisis. This is a period, if you look at the maps of the Mediterranean, then between Gibraltar and the north coast of Africa, there is a shallow sill there, so the water there is not very deep. At that time, sea level dropped to the point that it isolated the Mediterranean completely. There was no connection to the Atlantic. That was a period when evaporitic minerals, salts and everything formed in the Mediterranean. Sea level went down there, it went down here, and as you will see, it had a tremendous impact on the rocks on this island. Sea level came back up again in the basal Pliocene, and we got deposition of the Pedro-Castle Formation. And you see here that sea levels are bouncing all over the place. It becomes impossible for me to show this on this diagram. There is actually a time break between the deposition of the Pedro-Castle Formation and the deposition of the iron shore. I just simply can't show it on this diagram. So in the simplest sense, the geology of the island, as you see it here today, is simply due to sea level going down, coming back up, going down, coming back up. So I'm telling you this story about the Cayman Islands. You may say, well, okay, where's all your data? What is your database? Am I making this up? Well, my database is very extensive on this over the last 30 years. I got to update this. It's actually now about 34 years I've been coming down here looking at the rocks. I've looked at just about every rock outcrop there is. Some of those outcrops no longer exist because buildings have been built on top of them, which is great for me. Nobody else can get the rocks and can test my evidence. It buries them. Look at all these outcrops in the field, look at air photographs, and in addition, drilling of wells. Some of these wells have been drilled by the Water Authority, other wells I've had drilled. We've even drilled some of our own wells on the islands to get core and rock cutting samples. Got information now from about 120 wells that have been drilled. All my information on this is built into a big single database so that we can retrieve anything that we need. So let me show you what some of these rocks look like. This is on the north side of Cayman Brack at the east end. This is not the easiest place to get to. It's hot, My notebook refers to this as Death Cliff number 1. Because by the time I finished half a day's field work, I'm just about crawling back to the car. I look like a dead rat. And it's not a pretty sight. This is kind of brutal to go into this area on these hot days. There's the Brack Formation. There's the Cayman Formation. From reading Charles Matley's paper, he does not specifically say where he first landed on the Cayman Islands when he came here, but based on his description of the geology, I think this is the first place where he landed, based on what he talks about the rocks. And here, this is the boundary between the Brack Formation and the Cayman Formation. And remember before I showed you that picture of the surface of Cayman Brack, and I said that's a weathered surface. And this is what it looks like in the rock when I'm looking at a rock cliff face like that. It's just a line in the rock. And yet that line in this particular line in the rock here represents maybe 15 million years of time. So often these lines, when weathering has taken place, we've got more time represented by that line than we do by the rocks here and here. So we have to be careful when we're doing this. In this particular location, the Brack Formation is formed entirely of limestone. Cayman Formation is formed entirely of dolostone. If you go up to this boundary, put thumb here, finger here, cross that boundary, limestone, dolostone. It's that sharp a break. If we go to the south coast, we were on this south coast yesterday with Hendrik and some other people. It was hot. It was truly hot yesterday. One of the hottest days I've seen or experienced. And here we can see the Brack Formation, Cayman Formation. There's the boundary. And in case you ask me, how do I know that that boundary is the same one that I showed you on the north coast? Many years ago, I persuaded one of the local people on the Brack to take out a small boat, and he took me all the way around the island, and as I went around the island, I took photographs of the rock face and then was able to trace it around. That's the type of thing we do. This is still dolomite like it is on the north side, but here the Brack Formation has now changed. This is mostly dolomite here now. So we've got a change in rock type that we have to deal with. You'll see here the Brack Formation is full of caves, full of holes. And one thing that's very interesting here is that you see the roofs of the cave, such as this one here, the roofs are flat. You can see it here. If you go into the Great Cave on Cayman Brack, which is just off the edge of this picture, look up at the ceiling. It's a flat ceiling. This is somewhat unusual for caves, and it's a reflection of the fact that the caves are being dissolved and formed. They hit, the dissolution comes up to this point, and then for whatever reason, it's not dissolved in the basal part of the Cayman Formation here. If you go off in this direction, further up the coastline, you can actually find evidence of old springs. At one time, there must have been water flowing out along this unconformity, and there's evidence of the old springs. It's the only one I know of on the Cayman Islands. If you look at the rocks themselves, in terms of fossils, not the best fossils in the world. It's not somewhere I'd send you if you're a fossil collector. These are fossils here. This is a genus called Lepidocyclina. It's a big foraminifera. It's a single-celled organism. This particular one likes to live on the seafloor and sort of crawl around. This is in the limestone on the north coast. On the south coast, this is the dolostone. You notice that they look basically the same. And all these holes that you see in the rock are actually where these fossils used to be, but they've all been dissolved and lost. These are formed of aragonite. And remember I told you, if you start putting fresh water on the aragonite, they will dissolve. So you dissolve the fossils. Likewise, if you look here, this is on the south coast again. This is there is a little bit of limestone still on the south coast. And you look at these holes that are in here. These used to be bivalve shells or clam shells. The hinge line is there. The two valves would have been here and here. But all the shell material has been dissolved and gone. So if you're interested in collecting fossils, this is not the best place to go for fossils. The Cayman Formation typically looks like this. Cayman Formation is formed largely of dolomites. It's white. We have trouble knowing exactly how thick this is because there is no single place on the island where the entire formation is exposed. We're having some trouble in the wells of identifying boundaries. Best we know that this is about 120 meters thick. This red that you see here, this is the red soils. Geologically, we call these terra rosas. And the information, it's not work we've done, but other people have done, has shown that the material that forms the terra rosas probably does not originate on the Cayman Islands. It originates in the Sahara Desert. When you get a big sandstorm in the Sahara Desert, all the sand and particles get thrown up into the atmosphere. And they can show now with satellite pictures where these clouds of dust go across the Atlantic, get across into the Caribbean, and start settling down. And in some of the studies that have been done in the past, there's I can't imagine such an exciting research project where people go out with big nets, hold them up in the air, and try and catch these particles. It's a long time standing there to collect these particles. But when they do that, they can look at the minerals and they can match it back to the material in the Sahara Desert. So just as an aside. There's a lot of fossils in the Cayman Formation, except they're not terribly well preserved because you have to, when you look at fossils in the Cayman Formation, you've got to look at them in a reverse sense because all this shell material that was formed of aragonite has been dissolved. So you can see the gap going around here, this gap. This is where the shell material used to be. It's all been dissolved. This is the internal mold of the bivalve shell. Likewise here for this gastropod, same thing for this, well, coral, the whole coral has disappeared. I have seen on the Brack some of these coral heads that are up to 2 meters in diameter, 2 meters high. The entire skeleton has been dissolved, and you're just left with a hole in the rock. So again, it's kind of neat to collect these and these, but not the best place for fossil collecting. But what these fossils do tell us is that these rocks are originally sediments that formed in shallow water, probably no deeper than 30 meters. So it does give us that information. Bring you back to Grand Cayman, going to Padre Castle Quarry. Again, a photograph was taken some years ago. I was in there on Monday, and it's just so overgrown now you can't see these walls. But if you look at this wall here, if you look at it very carefully, you can see a line that cuts across here, light-colored rocks underneath, dark-colored rocks on top. This is, you saw this photograph before. This is the Cayman Formation, the Pedro Castle Formation, and the unconformity here. Take note of this unconformity because in the quarry, it looks as though it's a straight line. Please just remember that fact. If you look here, there are caves. We know from various techniques that these caves actually formed at the time when this unconformity was developing. So these caves are probably on the order of 5-6 million years old. In the Pedro Castle Formation, in terms of fossils, very similar to what you find in the Cayman Formation, branching corals, but all the original corals have disappeared. The one coral that you do find that's somewhat different are these peculiar looking corals. They're what we call a free living coral. These are single coral as opposed to colonial coral here. These are corals that are adapted to living on the seafloor in sand that moves around. Now, most corals, if you've got sand on the seafloor and that sand is moving around on the action of waves, the corals cannot live in it. It cannot tolerate it. This particular coral, there's a whole various genera of them, had developed the ability to do that. If you go in the Pacific Ocean today, you will see the same type of corals that can do that. In the Caribbean Sea, we do not see modern corals like this. The Iron Shore Formation looks like this. You're all familiar with it on the island. And if you go over to Cayman Brack, then you are familiar with the wave-cut notch that you see all the way around the island. This wave-cut notch is a height of 6 meters above sea level, and this is the sea level that was at 125,000 years ago. This is the sea level when much, not all, but most of the ironshore formation formed. So if you were here 125,000 years ago, sea level was 6 meters above where it is today. In terms of fossils, if you're a fossil collector, then this is the place to go. The fossils are beautifully preserved. The shells are still intact. Don't ask me how you get a truck here. I take students in the field, somebody produces a truck, and then tells me there's truckloads of fossils. Don't ask. But these are beautifully preserved. For example, we have found conch shells in the ironshore which still have some of their original coloration. They're 125,000 years old. We can still see the original color of the shell. Beautiful preservation. Go up onto the northwest corner of Cayman. Here are some of the corals that formed in the reefs, still in the original life position. Beautiful preservation. And again, the corals here. Now, I point out to you that we break this into formations. We can use this to show the distribution of formations across the island. Here is the Pedro Castle Formation, Cayman Formation, ironshore. We do not see the Brack Formation exposed at the surface here. And one of the questions that comes up is, well, what was it like in the past time? Well, one of the things we can do is we start here. It's a place what I call Paul Bowden Quarry. It's down just south of the cricket field. Going up through the cricket field, these are the sewerage works, Safe Haven, Little Salt Creek, and up to Hell. At Hell, where you see this phytokarst exposed, this is where the Cayman Formation is exposed. From all of these wells, and many others that we've got information from on this part of the island, we can track the top of the Cayman Formation. Remember I said that was an unconformity that formed when it was exposed to the atmosphere and weathered. And remember also in the quarry I showed you is that relatively straight line that you could see in the quarry wall. Well, when we track it across this part of the island, we find that this unconformity drops down. By the time you're about here, it's about 30 meters below sea level, and then comes back up towards Hell here. That's what the island looked like in that part of the world at that time. Sea level went back up, you get the Pedro Castle filling it in, and then the ironshore filling it in here. North Sound that sits here originated during this time. It's just that North Sound, the sediment hasn't completely filled it up as yet. If we go to Pedro Castle Quarry here, and then go into the lower valley where the lower valley waterworks are in here, and then out northwards across the island like this, then that same surface does that. So you get the impression from these two cross sections of a very irregular topography. And help you visualize this a bit more, we can look at the modern day topography of Grand Cayman. There's the mountain. This is again digital elevation model based on data from Lands and Survey. Higher land here, a little bit of high land around here and around Pedro Castle. I've got to play a bit of mental gymnastics with you here because this map is drawn that way, obviously going north. And when I show you this one, I've had to turn this around. But this is what the island looked like about 5 million years ago when you had exposure of the Cayman Formation and there was weathering. And on the west end of the island here, a big basin developed. And this is a scale of 60 meters. We know that this basin probably up to 40 meters deep. And then on the rest of the island, there was erosion, so not as severe. We're not quite sure why there was so much erosion here. It could have been something to do with rainfall patterns. Maybe there was more rain here at that time. We don't really know. We can't tell from the rocks. But this is what the island used to look like at about this time frame. If we look at the Cayman Brack, I've shown you this before, and here is the geology map of Cayman Brack. The bluff is formed mostly of the Cayman Formation. We've got the Pedro Castle Formation here. iron shore around the edge. If you look at a cross section, there is the Brack Formation. I cannot show the Brack Formation on the map because that's where you've got the vertical overhanging cliff faces, so it simply won't show up. But this is what the Cayman Brack looks like. So the question comes, why is Cayman Brack so different from Grand Cayman in terms of its geology? Think back to some of the early slides I showed you, in which I pointed out to you that Cayman Brack is probably on a different fault block than is Grand Cayman, than is Little Cayman. And with the work we've been doing in the last 4 or 5 years, we've been trying to get a better understanding of what has happened here. In a very cartoon-like fashion, showing Grand Cayman here, here's the Brack Formation, Cayman Formation, bearing in mind that this surface is going up and down, but for the sake of this diagram, I've simply drawn a straight line. This is typically about 120 meters below sea level here. If I go on to Cayman Brack, that same boundary between the Brack and Cayman is about 20 meters above sea level. And if you're wondering why I say about, if you trace the boundary around the east end of the island, it actually goes up and down a little bit. So it's about 20. So the differential, assuming that this will once look like this end of Cayman Brack has been uplifted by about 140 meters. The best we can tell is this uplift started about 3.5 million years ago and finished by 500,000 years ago. And during that time period, the island was being pushed up at a rate of about 4 millimeters per year. I mean, 4 millimeters per year, you say, that's very small. For the geologists, this is super fast. Think about it, if you're over 1 million years, that's 4 million millimeters, and so the numbers start adding up very quickly. And what you also have to realize is that as you push this up, then weathering is breaking down the rock at the same time. So a lot of the Cayman Formation has been lost from this end of the island. You've probably lost about 60 to 80 meters of that formation, being stripped away by erosion. We've lost all of the Pedro Castle Formation. It's simply disappeared. And this is why on Cayman Brack, the Cayman Formation is a wedge shape. You'll notice if you look at this diagram very carefully, it's at least twice the thickness, if not 3 times the thickness at the west end than it is at the east end. And that's because a lot of the rock being stripped away. Economic value. Why worry about all of this? If I show you that picture and ask you what you see there, you tell me you see holes in the rock. Great. I see money. Because for a geologist, the holes in the rock, that's where the oil, and that's where the gas, that's where the water and other minerals collect. And here on the Cayman Islands, of course, this is where it becomes valuable for the drinking water. So some years ago, I can't even remember when now, I'm getting old, I forget time. Hendrik phoned me up one day and said, I've got a job where I'd like you to look at this and help us out. We want to put in a reverse osmosis water plant at Lower Valley. This is where you're going to take seawater, convert seawater into fresh water, and away you go. And you say, well, why don't you just put a hose in the ocean and pull it out? Well, it's not that simple. You can't do it. And then he said, oh, by the way, we need to pull out 10,000 cubic meters of seawater each day, 7 days a week, 52 weeks a year, for year after year after year. So now we've got a problem. And then he added, you cannot damage the existing freshwater lens that's there. You can't damage any of the vegetation or the surrounding area. So you've got that problem. The next problem you've got is that if you take 10,000 cubic meters of seawater out, that produces 4,000 cubic meters of fresh water. It also leaves you with 6,000 cubic meters of brine. Because what you're doing is you're taking this 10,000 meters of seawater, you're pulling the fresh water out, you're leaving all the dissolved solids behind. So from a proportional point of view, you're increasing the salinity of this water. If you took that water and simply dumped it back in the ocean, Gina would be having a fit because we'd kill every coral in the country, because corals cannot tolerate these high salinities. And the other trick here is that once seawater's been processed, you cannot reprocess this brine. It's a one-shot deal. So we've got to get rid of that brine so it does not result in any contamination. It doesn't destroy the freshwater lens. It's going to have no impact on the corals around the island, and you cannot bring it back up into the situation again. So the process starts like this. The drill equipment comes out, we produce the core. This is 2-inch diameter core. My job as a geologist then is to look at this core and on the basis of that 2-inch piece of core, predict what is going to happen in a lateral direction all the way around this site. So that's where my knowledge of the geology of the island, I have to use that to try and make those predictions. We get porosity and permeability measurements to help us. On a theoretical basis, the maximum porosity in a rock, porosity is the percentage volume of air space in a rock. The theoretical maximum is about 49%. Because realize if you go to 51%, you've got nothing holding the rest of the grains up, they're all going to collapse. And notice here that some of these rocks we had tested, and I had these done in Canada by the same companies that deal with the testing for all the oil companies. They know what they're doing. We got values as high as 48%. And even the company that was doing this didn't believe it. They phoned me up and they said, we've done this 3 times because we don't believe it can be this high. They'd never seen such high porosity. I said, yeah, that's fine. So very high porosities here. In the upper parts of the Cayman Formation in this area, very low porosity. We then look at the permeability. Permeability is a measure of the ability of a rock to transmit fluids. If that is my piece of rock, in any piece of rock that I look at, there is usually a maximum direction of permeability, which we can assess. They then measure that direction. They then measure a direction at 90 degrees to that, and then we measure a vertical permeability. So we get 3 permeability measurements. Here, this is the horizontal, this is the maximum permeability, this is the permeability measured at 90 degrees to that, and you'll say, okay, sorry, this is the vertical permeability. I've cheated here. And you'll notice that most of the vertical permeability is about 0. One of the very strange features of the rocks on these islands, and I've seen it time and time again, is there's very little permeability vertically. I don't know why, we don't understand it. But on the basis of this, with Hendrik and the other engineers at Water Authority, we decided to put the abstraction zone here, disposal zone here, and there's the freshwater lens that we couldn't damage, and here's the top of the Cayman Formation, very low porosity, very low permeability, virtually no chance whatsoever of these waters going back up to infect and destroy the freshwater lens. So the geology worked for us perfectly here. Did this well work? Well, I'm still coming to the islands. The Water Authority still has me back, so the answer is yes. And in 1998, they started abstracting 3,750 cubic meters a day. And in 99, it went up to 7,500. Later in that year, went to 10,000 cubic meters a day. And it's been doing that ever since. It's not operational at the moment because the reverse osmosis plant got worn out. So they're putting a new plant in. But this shows you that underground here on this island, there is an incredible flow of water. You think about it, pulling out 10,000 cubic meters per day, day after day, year after year. Incredible volume of water. We've used the same technique looking at where they've put other reverse osmosis plants. Redgate, also on the north side near the Botanical Garden. One near the Botanical Garden is pulling out about 9,000 cubic meters a day, quite successfully. And you may think that because we've worked this out in Lower Valley, then we can simply take the same numbers and apply it to different parts of the island. It doesn't work like this on this island. This geology causes me nightmares at times because you can move a couple of kilometers and the rocks change and they behave differently. So every time you look at one of these new sites, we have to go through the same process and do the same evaluation. But fortunately, we can manage usually to get the answer. So in concluding, geological succession of the Cayman Islands formed as sea level has changed through time. Deposition took place when sea level was high. Erosion took place when sea level was low. The interplay between this, between periods of deposition and periods of erosion, is what controls the complex succession of rocks that you find on this island. Knowledge, I got to self-advertise. You need a geologist to help you understand what is going on with these rocks in the subsurface. And as the islands continue to develop, this is going to become more and more important. You can't just keep on dumping waste fluids or anything else down underground, because if you can't see it, it doesn't matter. On this island, potentially it does matter, and you're going to have trouble. And certainly we've demonstrated this with using the geological knowledge to help in the development, or at least set the groundwork and allow the water authority to come in and generate the water that you drink on a daily basis. And with that, I'm going to finish, and I thank you for your attention. If you have questions, I will gladly try and answer them. So thank you very much. Yes?
What is the potential of the landfill as it affects our water treatment?
You mean the current landfill? Well, that's a difficult question to answer. I'm not trying to avoid it, because as Hendrik would tell you, I never avoid a question. I don't know enough about the current landfill. I don't know, for example, if there's a liner at the base of it. No, there isn't. Then you've got potential of material leaching out from the landfill and going down in the ground and going into all the water that's under the island. How far it spreads, that's got to be worked out. In what sense about the future landfill?
Well, about what we can expect from that.
Well, it depends where, what happens in terms of where the government wants to put that landfill. But wherever they decide to put it, they better look at the geology underground first to make sure that you're not putting in you want to put it in an area in which the geology is working for you instead of against you. And there are certain areas on this island where it could work against you in a very bad way, or there are certain parts of the island where you could put it and it's going to help you. Now, with a lot of modern landfills, they can overcome this by using liners and other type of things. I'm not an expert in these areas. I know a little bit about it. But you still need to know about local geology to help you understand what you're going to do. Any other questions? Yes?
When you drill the wells and find this water that you're extracting by reversal osmosis, do you have any idea how old is this water?
I suspect that a lot of this water is very young, because if you're looking at Lower Valley Well, that is about most 2 kilometers from the nearest shoreline. And if you're pulling out 10,000 cubic meters a day, I suspect that my prediction is, and the reason we picked that layer, is that layer more or less goes straight out to the shoreline. So you're actually just allowing it to replace. The danger you've got when you're dealing with this sort of situation, you can drill a well anywhere, and you can start pumping out the water. The question is whether it will continue to allow you to pump out water, or if in 2 weeks' time it goes dry. So that's the real challenge. And given that proximity to the shoreline, I suspect there's a layer of about 50, 70 feet thick that goes straight out to the shoreline, and basically the tides are just pumping the water through. I cannot believe, yes?
The vertical drop and the vertical drop off, as we call it,
Yes.
is that all caused by being pushed up?
Yes. Well, it's a combination. You can see it here. There is the vertical cliff face, right? If I come back in this direction, come back towards the west end, and you know where you've got the platform where the iron shore sits on it, okay? If I drill through that platform, through the iron shore, I will hit the Brack Formation. And what we've been able to show there is that where you've got the bluff like that and you've got the platform sitting like that, the bluff comes down like that, and then there is a bench that cuts down like this and then drops off into the ocean. And this bench is cut into the Brack Formation. In some parts of the island, it's cut into the Cayman Formation. There appears to be in a period of time, and we do not know exactly what age, we suspect about 1 to 2 million years ago, when the island was being pushed up, but at the same time, sea conditions must have been quite different because there's this evidence of tremendous erosion of the coastal areas in which cut back the cliff faces and produce this ledge. We see exactly the same thing here on Grand Cayman. So it's a combination of the land going up and a combination of the erosion hitting the base of the cliffs, undercutting the cliffs, and it's collapsing down. And you can see the evidence for that over there. You can see in some of these areas where there's evidence of collapse of the cliffs. Yes?
Have you had the opportunity to go yourself or have other people done work on the Sierra Nostra in Cuba?
I have never been there. There is some information there, but not a lot. It'd be a very nice place to go to see if I can, see similar type of things. But there's only so many days in the year, and I'm involved in field work, not just here, but in other parts of the world as well. I'm kept busy now. Yes?
Apparently we had an earthquake here today.
Oh, did we?
How large it was, 4.6, and we had two about, I don't know, maybe 3 weeks ago or so.
Boy, I wish I'd felt that one today. The reason I say that, I was talking to some of the school children today, and I was talking about earthquakes, and I said to them, what time did that happen, do you know?
About 2:30, I think.
Well, that was about right at the same time as I was asking the students, have you felt an earthquake? So it had been quite appropriate if the earthquake had been felt by all of us in the school at that time, but that's interesting. Yeah.
So, my concern, sometimes I'm a bit dramatic, but, are we in danger?
Well, let me put it this way. It's the same thing I explained to the school. If you go to the west coast of North America, the San Andreas Fault. The San Andreas Fault is exactly the same type of fault as the Orient Transform Fault that you've got here. And what happens with the San Andreas Fault is that you've got North American plate moving this way, you've got the Pacific plate going this way. And while things are just moving along, that's great. But in that particular area, it's not just one fault, there's a whole group of faults. And we know that in the subsurface, the rocks get locked in place. So if you can imagine, watch my thumbs, the plates do this, and they lock up. And of course, everything's quiet, and people say, oh, the fault's no longer active. Well, that's the wrong attitude, because 100 years time, 200 years time, you've still got the pressure being applied this way, pressure. It eventually breaks that lock point and does that. And when it does that, that's when you get the massive earthquakes. On this fault that you've got here, I'm not saying it's impossible to have that sort of magnitude. The Earth does what it wants to do. But the fact that you're getting very small earthquakes almost on a weekly basis, the fact that you're getting earthquakes like today, apparently at 4, earthquake about 4, you're not really going to feel it. So that's the good news, because while it's doing that, it's telling you the faults are moving apart, you're releasing the pressures. So if it keeps on doing that, you should be happy. I just hope that next week there's not a 9. I'll never be able to come back here again. I'll be back in Alberta. No, seriously, it's while it's doing that little movements, you probably, if somebody said to me, you've got to go and live by a transform fault, and you've got a choice, it's either the San Andreas Fault or this one, I'd come to this one. Yes?
Brian, the thing with all one of these huge boulders,
Yes.
along the south coast,
Right.
like
Yep. Yeah.
How's it taken to that?
Those boulders, and these are the boulders that you see along the coastline by Pedro Castle, as Fred has indicated, and just this side of blowholes. Those happen to be in two areas of the coastline where you've got no offshore reef. We have looked at those. We've estimated that the weight of some of those boulders is as much as 10 tons, huge boulders. And we got lucky quite a long time ago in that all of those boulders are formed of Cayman Formation, the dollar stones of the Cayman Formation. On one of the boulders, we actually found relatively modern corals growing on the boulder. We found lithophagid borings telling us that this boulder used to be in the ocean and it wasn't very long ago. When we dated the corals, we got an age that took us back to about, in simple terms, about 660 AD, which happens to be just before the first record of human habitation of these islands. So we know that those boulders at that time were in the open ocean, because we know that sea level was not up that high. We've estimated, and it's a crude estimate, that those boulders have been lifted by 6 to 8 meters vertically and anywhere up to 100 meters laterally. There is one of two ways that that's happened. It was either a super hurricane or it was a tsunami. And what was really interesting, in case you're wondering, you say, well, how can a hurricane move these boulders? Last year when I came down here to talk to the schools, some of my older photographs were not very good, so I said to Henrik, we need, on the way to this Clifton Hunter School, I want to stop, run out, and take a photograph of this one boulder that I know that has these modern corals on. And I have a fairly good memory of where things are. And I couldn't find the boulder. And I thought, And of course, being forgetful like I am, I'd forgotten to take my map out because we've mapped all those boulders in over the years. I went back and checked the map and it was exactly where I thought it was supposed to be. Went back out there and discovered that the boulder had been moved maybe 5 or 10 meters, but it had also been turned upside down. And then when I started looking at some of the others, they'd been moved. Now, the immediate reaction would be, well, maybe somebody's been in there with a bulldozer. There was no evidence for that. But what you could see evidence of was these boulders, look, they've been pushed across the land. We think Hurricane Ivan. It's just pushed these over. So it gives you an idea of the force of it. Whether they're originally because of a hurricane or a tsunami, I'm not sure, because we've got no other records to back it up. Any other questions? No?
Reference to a difference in level of sea.
Yeah.
What could have precipitated the level of the sea being that high at that time 100 years ago?
You mean for the pushing the boulders?
No, not
Or any yeah. Why? In other words, why does sea level go up or sea level come down? Sea level, there's a number of ways you can do this. The easiest way of thinking about it, and the most common cause, is it's related to periods of glaciation. So if you get a period when the ice caps start expanding, then in order for the ice to expand, you've got to have more water. And those ice caps expand by taking water out of the ocean. If you take water out of the ocean, you drop sea level. And now on the reverse, if we melt that ice cap, then sea level is going to go up. And for example, today, there's quite a lot of evidence on balance. You all hear about, the ice caps are shrinking, the glaciers are retreating, they're melting, sea level is going up very slowly. So that's the main trigger. There's a couple of other reasons why you can get change, but that'd take me a bit longer to explain. But fundamentally, the ice that's the most important thing. Okay? There's certainly that sea level 125,000 years ago when it's 6 meters above sea level. We can tie that into a period of increased size of the ice caps. When we get back into 30 million years ago, it's a bit more difficult to do it, but you can still do it. Okay, thank you for your attention.
Please feel free to take any food and use left over. And we also have a few books on
Yes?
Little mentions a lack of data in Little Cayman. That's where I grew up.
Right.
It's just because you have not.
Yeah, we just haven't worked there. In fact, I was talking to Hendrik about this yesterday and today. We've got to start trying to do some work there because I've only ever been on Little Cayman once. And the problem is there's so little rock exposure there that basically we're going to have to go over and drill it at some point to get the information.
Second question, you mentioned that